So welcome students. In this video, we are going to look at the properties of modulus. So let us start with the most important properties and go one by one. So the first property of modulus and the most important one is z conjugate z into z bar is equal to mod z whole square. If you multiply z and z bar, you get mod z whole square. This is very straightforward. Z if you take it as x plus iy and z bar if you take it as x minus iy. So what is x plus iy into x minus iy? This is x square minus iy whole square. So iy whole square is minus y square. So minus of minus y square becomes x square plus y square. And this is equal to root of x square plus y square whole square, right? And root of x square plus y square is nothing but mod z. So that is equal to mod z whole square. So z into z bar is equal to mod z whole square. So it doesn't need to be z here. Any complex number multiplied by its conjugate gives you its magnitude square. This property will be useful whenever you need to calculate the moduluses of complex numbers. So next property is z1 z2 modulus is equal to modulus of z1 z2 is equal to mod z1 times mod z2. So if you have two complex numbers, you multiply them and take the modulus. Just take the modulus and multiply them. Both answers will be same. So this can be proved from Euler form of complex number. If you take z1 is equal to r1 into e power I theta 1, where r1 is the modulus, theta 1 is the argument. And if you take z2 is equal to r2 e power I theta 2, r2 e power I theta 2. So what is z1 into z2? z1 into z2 is, you just need to multiply these two. So r1 and r2 are real numbers. So they get multiplied separately, r1, r2 times e power I times theta 1 plus theta 2. So theta 1 plus theta 2 became the argument. And the number which is outside e power I theta is nothing but r1 into r2, which is nothing but the magnitude of z1 into z2. So mod of z1 into z2 is equal to mod z1 into mod z2. This is a very important property. Let us see how to apply this when we deal with problems. So the next property is modulus of z1 by z2 is equal to mod z1 by mod z2. You can separate the modulus over division. You can separate the modulus over multiplication. So this can also be seen from the Euler form. So what is z1 by z2? This by this. So r1 is real, r2 is real. So they combine to give you r1 by r2 times e power I times theta 1 minus theta 2. So what is the magnitude part? The magnitude part is r1 by r2. That's nothing but modulus of z1 by modulus of z2. So if you are careful, you can also observe what is happening to the argument part, which we'll deal with later. So when you multiply two complex numbers, their magnitudes are getting multiplied, their arguments are getting added. So when you divide two complex numbers, their magnitudes are getting divided, their arguments are getting subtracted from one another. So mod of z1 by z2 is mod z1 by mod z2. And a similar property is mod of z power n is equal to. So if you raise z to something like 100 power, so you're given some z and you raise it to 100 power and take the mod. So this will be exactly same as mod z whole power n. This can also be proved very easily. If z is taken as r times e power I theta, what is z power n? Z power n is r times e power I theta whole power n. So from the laws of indices, this is r power n times e power I n theta. So what happened to the magnitude? It's just magnitude of z power n. So mod of z power n is equal to mod z whole power n. And you can also look at what is happening to the argument. What is argument of z power n? N times argument of z, which we'll see later. So I hope the first four properties are very clear to you. These are the most important properties. Z bar is equal to mod z whole square. Mod of z1 z2 is mod z1 into mod z2. This can be extended. Mod of z1 z2 z3 is mod z1 into mod z2 into mod z3. So you can see why this can be extended from the derivation. Even if you have another complex number, the moduluses are getting multiplied when the complex numbers are multiplied. So what is mod of z1 by z2? Mod z1 by mod z2. What is mod of z power n? Mod z whole power n. Now let us go forward. So the next set of properties deal with calculation of moduluses of complex numbers. So the next property says that mod of z1 plus z2 whole square. So if you add two complex numbers and then take modulus whole square is equal to mod z1 square plus mod z2 square plus 2 times real part of z1 z2 bar. And mod of z1 minus z2 whole square is equal to mod z1 square plus mod z2 square minus 2 times real part of z1 z2 bar. So these are the two properties which deal with moduluses of sum of two complex numbers. So let us see how these are happening. So this property can be derived using the first property that we have seen. So what is modulus of z1 plus z2 whole square? This is nothing but z1 plus z2 times z1 plus z2 whole bar. We know that z times z bar is equal to mod z whole square. Some complex number times its conjugate is equal to modulus of complex number whole square. So that is equal to z1 plus z2 times z1 bar plus z2 bar, because from the properties of conjugate we have seen that conjugate can be separated. So that is equal to, now this is complex number multiplication, just need to expand the brackets, right? So z1 into z1 bar is nothing but mod z1 whole square. z1 into z2 bar is nothing but z1 z2 bar. Next z2 z1 bar. And z2 into z2 bar is mod z2 whole square. So that is equal to mod z1 square plus mod z2 square plus z1 z2 bar plus z2 z1 bar. So can you see that these two are conjugate to one another? So what is z1 z2 bar whole conjugate? Z1 conjugate into z2 double conjugate, which is z2. So these two are conjugates of one another. So a complex number plus its conjugate gives you 2 times the real part of complex number. So that is equal to 2 times real part of either z1 z2 bar can be written or z2 z1 bar can also be written. So you can write whatever you want, both will be same. Real part of z1 z2 bar will be same as real part of z2 z1 bar, because both are conjugate to each other. So z1 plus z2 whole square is equal to mod z1 square plus mod z2 square plus 2 times real part of z1 z2 bar. Now similarly you can also prove this. I'm not going to prove that because you just need to put a minus sign here, so you get minus signs here. So the next property closely related to this is modulus of z1 plus z2 whole square is equal to mod z1 square plus mod z2 square if. So when will modulus of z1 plus z2 whole square be equal to mod z1 square plus mod z2 square? Obviously from this formula, if this has to happen, then real part of z1 z2 bar has to be equal to 0, right? So if this is equal to 0, then modulus of z1 plus z2 whole square will be equal to mod z1 square plus mod z2 square. That is, what is the meaning of this? That means z1, z2 bar is purely imaginary, right? A real part is equal to 0 means that the complex number is purely imaginary. That implies, so if a complex number is purely imaginary, what is the meaning of that? That is, z bar should be equal to minus of z. That is what we have seen in the topic of conjugates. If a complex number is purely imaginary, z1, z2 bar whole bar has to be equal to minus of z1, z2 bar. So this implies z1, z2 bar whole bar is nothing but z1 bar z2 is equal to minus z1 times z2 bar. And that implies z1 by z2 is equal to z1 by z2 is equal to minus of z1 bar by z2 bar is nothing but minus of z1 by z2 whole bar. So z1 by z2 whole bar is equal to minus of z1 by z2, which implies z1 by z2 is purely imaginary. So this will be the final condition which we are looking for. So if z1 plus z2 whole square is equal to mod z1 square plus mod z2 square, this will happen if z1 by z2 is purely imaginary. Now the next property is also related to these two formulas, so which is the addition of these two. What is mod of z1 plus z2 whole square plus mod of z1 minus z2 whole square? So what is the addition of these two? If you add these two terms get cancelled. So this will be equal to 2 times mod z1 square plus mod z2 square. So z1 plus z2 whole square plus z1 minus z2 whole square is 2 times mod z1 square plus mod z2 square.